The goal for this research was to understand some biological results we obtained from a field study of hatchling sea turtles and how they move across granular materials. A student working in my group, Nicole Mazouchova, went out to the beaches of Jekyll Island, Georgia, and performed locomotion experiments on hatchling sea turtles. And one of the remarkable things she found was that the animals are in fact quite effective at moving over a diversity of grounds. Nicole noticed a very interesting feature of the movement of these turtles when they were running at several body lengths a second down the loose sand. She found that they tended to bend their wrist in a particular and interesting way, and we developed a hypothesis that the wrist movement patterns that we observed were useful somehow for allowing them to transit the loose material with effectiveness comparable to what they'd move on hard ground. One way we could test this hypothesis was to build a model of a turtle, but increasingly we build things called physical models, which look like robots, but function for us as devices for which we can vary parameters and test things carefully and repeatably over a wide range of conditions. The sea turtles we found moved quite effectively when they bent their flipper limbs at the wrist and propelled themselves forward. And we found that the sea turtle robot on average performed better when we allowed it to bend its wrist. In addition, a flexible wrist allowed the flipper to remain locked in place, in contrast to a fixed wrist, which created a yielding material, a flowing material around the wrist, which caused the robot to sink into the ground as it moved forward. Based on this, we then did what is a theme in my group and used the model to make a prediction about what we might observe in the actual organisms themselves. The predictions that were made by the robot model gave us some insight into the failure mechanisms for actual biological organisms. And in my group, this is what we count as a success story. This is when we are happy, when a model has some utility for helping us not only describe what we see in the natural biological world, but to try to predict what we might see and then see if we can confirm that prediction. The insights we've gained from studying simple limb-ground interactions adds to the suite of behaviors and limb shapes and controls that robotic designers can use to create all-terrain robots.